Tonight, we're going to explore one of the strangest truths hidden inside the universe. Every moment of every day, light is pushing on everything around you. The sunlight warming your skin is not simply delivering energy, it is exerting a tiny physical force. The light from distant stars is pressing outward into space. Every photon leaving your phone screen, every beam from a flashlight, every ray escaping the sun is carrying something that, according to everything we learn in school, should be impossible: momentum. At first, that sounds perfectly ordinary. After all, momentum is simply what moving objects possess. A speeding car has momentum. A baseball thrown across a field has momentum. A freight train rolling down the tracks has momentum so enormous that bringing it to a stop requires tremendous force. But every one of those examples has something in common. They all have mass. For centuries, that connection seemed inseparable. If something could push another object, it had to contain matter. Something heavy had to collide with something else. Momentum belonged to physical substance. It belonged to objects you could hold, weigh, or touch. Then light ruined the picture, because light has no mass, not almost none, not an unimaginably tiny amount, exactly none. A photon possesses zero rest mass. This is not an approximation. It is one of the most precisely tested facts in modern physics. Every experiment ever performed agrees with it. If photons possessed even the slightest amount of rest mass, the universe itself would behave differently. Radio waves would travel at different speeds from visible light. Electromagnetic fields would spread differently through space. Countless experiments would have revealed the discrepancy long ago. Instead, nature insists on something that appears almost contradictory. Light has no mass, and yet light pushes. Not metaphorically, literally. A beam of light can move an object. It can twist mirrors suspended inside laboratories with astonishing precision. It can push atoms through space. It can steer microscopic particles using nothing more than carefully focused laser beams. It shapes the magnificent tails of comets, stretching millions of kilometers across the solar system. It slowly accelerates spacecraft equipped with enormous reflective sails. Inside the most massive stars in existence, light itself helps prevent gravity from crushing those stars under their own unimaginable weight. All of this happens because photons carry momentum. How can that be? If you stopped almost anyone on the street and asked them what gives something the ability to push another object, they would probably answer with confidence: mass. After all, every experience in daily life teaches exactly that lesson. A bowling ball knocks over pins because it has weight. A hammer drives a nail because it is heavy. A truck crushes a smaller vehicle because it carries enormous mass. Everything we observe seems to reinforce the same simple picture. To move something else, you must first possess material substance yourself. Light appears to violate that rule entirely. Imagine standing outside on a warm summer afternoon. Millions upon millions of billions of photons are arriving from the sun every second, crossing roughly 150 million kilometers of empty space before reaching your body. You feel warmth, you see brightness. Perhaps you even close your eyes because the sunlight is too intense. What you do not notice is that every one of those photons is delivering an impossibly tiny push. Individually, each push is so small that no human nervous system could ever detect it. Together, the force remains extraordinarily weak, yet it is absolutely real. If you placed an exquisitely sensitive instrument beneath a beam of sunlight, it would register that force. If you removed every competing influence, air currents, thermal expansion, vibrations, even tiny seismic movements, you would eventually watch light physically move matter. This is not science fiction. It is experimental physics. The realization completely transformed how scientists understood motion itself. Because once you accept that light carries momentum, an uncomfortable question immediately appears. Perhaps momentum never truly belonged to mass in the first place. Perhaps we misunderstood the relationship entirely. That possibility is surprisingly difficult to accept because our brains evolved in a world where everything meaningful moves far below the speed of light. We have never watched photons collide with everyday objects. We have never thrown beams of light across a room instead of baseballs. Our intuition was built from rocks, rivers, trees, wind, falling apples, rolling carts, swinging doors, and crashing waves. Every one of those phenomena involves matter. Nature quietly hid a deeper rule beneath experiences that seemed obvious. The history of physics is filled with moments exactly like this. Again and again, scientists believed they understood reality because the visible world behaved consistently. Then someone asked an uncomfortable question. What if the pattern we see is only a special case? The Earth appears motionless, until it isn't. Time appears universal, until it isn't. Space appears absolute, until it isn't. Momentum appears to require mass, until light enters the conversation. That pattern repeats throughout the history of science, because the universe rarely reveals its deepest rules through ordinary experience. Instead, it hides them behind extremes: the unimaginably fast, the unimaginably small, the unimaginably energetic. Light belongs to all three. For thousands of years, people viewed light as something almost mystical. It illuminated the world while remaining strangely untouchable. You could see it, but never grasp it. It traveled through empty space without slowing down. It arrived from distant stars after journeys lasting thousands or millions of years. It carried information across the cosmos, revealing places humanity could never visit. It seemed almost ghost-like, something that revealed reality without participating in it. But modern physics uncovered a far stranger truth. Light is not merely observing the universe. It is constantly interacting with it. Every photon exchanged between objects transfers energy. Every transfer of energy carries momentum. Every exchange subtly reshapes reality. The walls surrounding you are continuously absorbing photons. Your eyes detect light because photons collide with molecules inside your retina. Leaves convert sunlight into chemical energy because photons strike electrons inside chlorophyll. Entire planets receive a continuous stream of momentum from their parent stars. The universe is engaged in an endless conversation, made not only of energy, but of tiny exchanges of motion, occurring trillions upon trillions of times every second. And almost nobody notices. Perhaps the strangest part is that this story does not begin with Einstein. Most people assume Einstein solved every mystery involving light, but the puzzle appeared long before relativity existed. Astronomers noticed curious behavior among comets. Physicists struggled to understand electromagnetic waves. Mathematicians discovered equations predicting something they could scarcely believe. Experiments produced results that contradicted centuries of accepted wisdom. Each discovery added another piece to a puzzle that seemed impossible to assemble. How can something with absolutely no mass carry momentum? The answer would eventually require rewriting humanity's understanding of space, time, energy, matter, and motion itself. It would force physicists to abandon ideas that had survived for over 200 years. It would reveal that one of the most familiar equations taught in every classroom tells only part of the story. Because the universe is under no obligation to follow human intuition. It follows mathematics. And the mathematics was about to reveal that mass had never been the true source of momentum at all. Mass was simply one way, perhaps the most familiar way, for the universe to store energy. Light had discovered another. As tonight's journey unfolds, we'll slowly peel away layer after layer of this mystery. We'll follow the path from Newton to Maxwell, from Einstein to quantum mechanics, from laboratory experiments measuring impossibly tiny forces to spacecraft sailing on sunlight itself. By the end, the question will no longer be how light can push without mass. The far more astonishing realization will be that mass was never the essential ingredient we thought it was. Because beneath everything you've ever pushed, thrown, caught, or watched move across the universe lies something even more fundamental. Not matter, not weight, but energy itself. If you ask someone to define momentum, the answer usually comes quickly. Momentum is mass times velocity. It is one of the very first equations students memorize when they begin studying physics. Simple, elegant, easy to calculate. Take the mass of an object. Measure how fast it is moving. Multiply the two together. The result tells you how difficult that object will be to stop, or how much motion it can transfer when it collides with something else. For everyday life, the equation works beautifully. A bowling ball rolling toward a set of pins carries far more momentum than a tennis ball moving at the same speed because the bowling ball contains much more mass. A speeding bullet carries enormous momentum, despite its small size, because its velocity is so high. A freight train moving surprisingly slowly can still possess overwhelming momentum because of its incredible weight. Everything fits the equation. Everything agrees with experience. For more than 2 centuries, nobody had any reason to doubt it. In fact, momentum became one of the most fundamental ideas in all of classical mechanics. It wasn't merely a convenient calculation. It was considered a fundamental property of moving matter itself. When 2 billiard balls collide across a table, something remarkable happens. The first ball slows down, the second ball speeds up. Momentum hasn't disappeared. It hasn't been created from nothing. It has simply moved from one object into another. This simple observation became one of the deepest conservation laws in all of physics. The total momentum inside a closed system never changes. It can change owners. It can be redistributed, but it cannot simply vanish. Imagine throwing a baseball against a brick wall. The ball strikes the wall and rebounds backward. During that brief collision, something invisible but very real has occurred. The ball changes direction. Its momentum changes. For that to happen, the wall must receive an equal and opposite amount of momentum. Even though the wall hardly moves, the Earth itself absorbs the tiny recoil. Every collision, every push, every explosion, every rocket launch, every falling raindrop obeys exactly the same rule. Momentum is always conserved. The universe keeps perfect accounts. Nothing is ever missing. Nothing is ever added without explanation. That principle became one of the cornerstones of physics because it seemed to describe absolutely everything. When a rocket launches into space, enormous quantities of hot exhaust gas are expelled downward. Those gases carry momentum in one direction. The rocket gains equal momentum upward. The total remains perfectly balanced. When a cannon fires a cannonball, the cannon recoils backward. When a swimmer pushes water behind them, they move forward. When birds flap their wings, when helicopters spin their rotors, when fish push against water, when humans simply walk across the ground, momentum is quietly flowing between objects. Everywhere physicists looked, momentum appeared inseparable from matter. There was always something physical doing the pushing. A hand, a wheel, a molecule, a stream of water, a cloud of gas. Never anything weightless. Never anything with zero mass. That wasn't merely coincidence. It shaped the way scientists thought about reality itself. Isaac Newton formalized much of this picture in 1687 when he published one of the most influential books ever written, Philosophia Naturalis Principia Mathematica. The Principia didn't simply introduce new equations. It introduced an entirely new way of seeing the universe. Instead of viewing nature through philosophy alone, Newton described it through mathematics. Objects moved according to precise laws. Forces produced acceleration. Gravity governed planets and apples alike. The same equations explained the moon orbiting Earth and a stone falling from a tower. It was a breathtaking achievement. For the first time in history, the heavens and the Earth obeyed the same rules. Within Newton's framework, momentum naturally belonged to mass. After all, if force changes momentum and force acts upon matter, then matter appeared to be the carrier of momentum itself. Nothing in everyday experience contradicted that conclusion. The idea became so deeply embedded in science that few people even questioned it. It simply seemed obvious. If something has no mass, how could it possibly possess momentum? How could it possibly push? Imagine trying to throw a shadow, or catch a rainbow, or lean against darkness. The idea feels absurd because those things possess no substance. Light appeared similar. It illuminated objects but seemed incapable of acting like one. You could shine a flashlight across an empty room. Nothing visibly moved. The walls remained perfectly still. Dust settled exactly where it was. The beam appeared to pass through space without disturbing anything around it. Compared to the enormous forces of gravity or physical contact, light seemed completely powerless. If someone in Newton's time had suggested that sunlight could someday push spacecraft across the solar system, they would almost certainly have been dismissed as fantasists, not because the idea sounded slightly unlikely, because it directly contradicted everything known about mechanics. And yet, nature had quietly been displaying the evidence for centuries. Every morning, sunlight left the sun carrying momentum. Every afternoon, photons struck Earth, transferring tiny amounts of that momentum into our planet. Every comet drifting through the solar system slowly revealed the same secret. Nobody simply knew how to interpret it. Part of the problem was scale. Human intuition completely fails when forces become unimaginably small. Imagine placing a single grain of sand on the palm of your hand. You can barely feel its weight. Now imagine dividing that weight millions upon millions of times. That begins to approach the pressure exerted by ordinary sunlight on the same area. It is so incredibly weak that almost every other force overwhelms it. A gentle breeze, a tiny vibration, the expansion of metal caused by temperature changes, even the random movement of air molecules. All of these effects are vastly larger than the push of ordinary light. For centuries, there simply existed no instrument delicate enough to isolate such a tiny force. And so light continued hiding its secret in plain sight. Not because the evidence wasn't there, because humanity lacked the precision required to notice it. Physics often advances exactly this way. The universe isn't waiting for dramatic revelations. It quietly behaves according to its own rules. The limitation lies with us. As our instruments improve, reality slowly reveals another layer. A telescope uncovers moons around Jupiter. A microscope reveals living cells. A particle detector exposes invisible subatomic particles. A sufficiently sensitive experiment eventually reveals something even stranger. Light pushes. Long before scientists could explain why, they began encountering hints that something unusual was happening. Astronomers noticed that comet tails behaved oddly. Physicists studying electricity discovered equations with unexpected consequences. Mathematicians found solutions that predicted entirely new phenomena. Each clue pointed toward the same impossible conclusion. Somehow, something completely massless was carrying momentum through empty space. At first, almost nobody believed it. The equations suggested it. Nature hinted at it. But common sense rejected it. Because common sense had been trained inside a world where everything that pushed also possessed weight. The universe, however, has never been particularly interested in protecting human intuition. And very soon, one of history's greatest mathematical discoveries would force physicists to confront an unsettling possibility. Perhaps light wasn't breaking Newton's laws at all. Perhaps Newton's famous equation had simply never been the whole story. Long before anyone could explain why light carries momentum, nature had already begun leaving clues. The evidence wasn't hidden inside laboratories. It wasn't buried in complicated mathematics. It was hanging in the night sky for anyone patient enough to notice. Every time a comet appeared, it quietly demonstrated that light was doing something no one believed possible. To appreciate why this mattered, imagine standing beneath a perfectly dark sky 400 years ago. There are no satellites, no electric lights, no telescopes powerful enough to reveal distant galaxies. The stars dominate the heavens with astonishing clarity. Occasionally, something unusual appears. A glowing visitor stretches across the sky with a magnificent, luminous tail trailing behind it. To ancient civilizations, comets often seemed like omens. To astronomers, they were mysteries waiting to be understood. Among those astronomers was Johannes Kepler. Today, he is remembered primarily for discovering the laws governing planetary motion. But Kepler was also an extraordinarily careful observer of the heavens. While studying comets during the early 17th century, he noticed something peculiar. No matter where the comet traveled, its tail always pointed away from the sun. At first glance, that might not seem surprising. After all, illustrations of comets almost always show beautiful tails streaming behind them. But if you think carefully about it, that isn't actually what happens. Imagine driving a car through heavy rain. The spray trails behind you because your motion carries it backward. If a comet behaved similarly, its tail should simply trail opposite its direction of travel. Sometimes that would point away from the sun. Other times, it would point toward it. It would depend entirely on the comet's orbit. But that isn't what Kepler observed. Whether a comet was falling inward toward the sun or racing outward after swinging around it, the tail stubbornly continued pointing away from the sun itself. It behaved as though something located at the sun were constantly pushing on it. Kepler proposed a remarkably bold idea. Perhaps sunlight itself was blowing the comet's tail outward. He had absolutely no mathematical theory explaining how such a thing could happen. He knew nothing about photons, nothing about electromagnetic waves, nothing about momentum carried by light. He simply trusted what the heavens appeared to be telling him. The sun seemed to be exerting a pressure. Today we know that Kepler was astonishingly close to the truth. Modern comets actually possess two different tails. One consists mainly of electrically charged gas. The other consists of microscopic dust particles released as sunlight warms the comet's icy surface. These two tails form for different reasons. The glowing blue ion tail is shaped primarily by the solar wind, a continuous stream of charged particles flowing outward from the sun. But the broad, graceful dust tail, the one Kepler spent so much time observing, is pushed largely by radiation pressure. The momentum carried by sunlight gradually accelerates countless microscopic dust grains away from the sun. Each individual photon contributes almost nothing. Each individual dust grain receives an almost unimaginably tiny push. But the process never stops. Hour after hour, day after day, week after week, the photons continue arriving. Momentum continues accumulating. Eventually, the effect becomes impossible to ignore. An enormous luminous tail stretches millions of kilometers through space. One of the most beautiful objects visible in the night sky owes part of its existence to the fact that massless light carries momentum. Yet in Kepler's time, this explanation sounded almost impossible. How could something completely weightless push anything? No one possessed an answer. For more than 2 centuries, the mystery remained unresolved. The observations were undeniable. The explanation simply did not exist. This often happens in science. Nature provides the answer first. Human understanding follows much later, sometimes centuries later. Kepler could describe what happened. He could not explain why. Meanwhile, physics itself was changing. Throughout the 18th and early 19th centuries, electricity and magnetism became increasingly important areas of research. At first, they appeared unrelated. Electricity involved sparks, batteries, and flowing charges. Magnetism involved compass, needles, and mysterious attractive forces. Researchers studied them as separate phenomena. Gradually, strange connections began appearing. Electric currents created magnetic fields. Moving magnets generated electric currents. The two subjects seemed strangely intertwined. No one fully understood why. Then came one of the greatest intellectual achievements in scientific history. A Scottish physicist named James Clerk Maxwell succeeded where everyone else had failed. Instead of viewing electricity and magnetism as separate forces, he united them into one elegant mathematical framework. His achievement cannot easily be overstated. Newton had unified falling apples and orbiting planets. Maxwell unified electricity, magnetism, and light itself. He wrote down 4 equations. At first glance, they appear almost deceptively simple, yet hidden inside them was an entirely new picture of reality. According to Maxwell, electric fields and magnetic fields were not independent things. Each could create the other. A changing electric field produced a magnetic field. A changing magnetic field produced an electric field. Once this process began, the two fields could continually regenerate one another. An electric field created a magnetic field. The magnetic field created another electric field. The cycle repeated endlessly. The result was something extraordinary. A self-sustaining wave traveling through space. Not a wave moving through water, not a wave moving through air, a wave existing within the electromagnetic field itself. When Maxwell solved his own equations, he calculated how fast these waves should travel. The answer shocked him: approximately 300,000 kilometers every second, exactly the measured speed of light. Suddenly, one of the oldest mysteries in science received an astonishing answer. Light wasn't merely something emitted by glowing objects. Light itself was an electromagnetic wave. Visible light became only one tiny region within an enormous electromagnetic spectrum. Radio waves, microwaves, infrared, visible light, ultraviolet, X-rays, gamma rays, all of them turned out to be the same phenomenon. Only their wavelengths differed. It was a breathtaking realization. Yet Maxwell's equations contained another prediction that attracted far less attention, one that seemed almost absurd. The mathematics suggested these electromagnetic waves did not merely carry energy. They also carried momentum. If an electromagnetic wave struck a surface, it should exert pressure. Not metaphorical pressure, real physical pressure. Enough to push, enough to transfer momentum, enough to move matter itself. Maxwell wasn't guessing. He wasn't proposing philosophical speculation. The prediction emerged directly from the equations. If the mathematics describing electromagnetism was correct, then light had to push. There was no escaping the conclusion. Unfortunately, the predicted force was almost unimaginably small. For ordinary sunlight reaching Earth's surface, the pressure amounts to only a few millionths of a Newton per square meter. That is so tiny, it disappears beneath almost every other disturbance imaginable. A faint breath of wind, the expansion of metal caused by warmth, tiny vibrations traveling through the ground, even random collisions between air molecules. All of these effects overwhelm the pressure of ordinary light. The prediction, therefore, created an awkward situation. The equations demanded that light push, but no experiment could yet prove it. Many scientists admired Maxwell's mathematics, while quietly wondering whether this particular prediction might simply be too strange to believe. Could equations really overturn more than 200 years of intuition? Could momentum truly exist without mass? The universe seemed to be whispering yes. Comets hinted at it. Maxwell's equations demanded it. But physics was still waiting for someone capable of demonstrating it beyond all doubt. And when that moment finally arrived, it would force scientists to abandon one of their oldest assumptions forever. Predicting that light should push on matter was one thing. Proving it was something else entirely. Mathematics can be elegant. Nature can still refuse to cooperate. Maxwell's equations insisted that every beam of light carries momentum, but the force they predicted was so unimaginably small that it seemed almost impossible to measure. Imagine trying to detect the weight of a single grain of sand while standing in the middle of a hurricane. That is roughly the challenge physicists faced. Every experiment had to eliminate countless other effects that were millions or even billions of times stronger than the pressure of light itself. Air currents, temperature changes, mechanical vibrations. Even the expansion of metal caused by slight warming could completely overwhelm the tiny force they hoped to observe. For years, the prediction remained just that, a prediction. Then, during the 1870s, an English scientist named William Crookes believed he had finally found the proof. His invention became one of the most famous scientific instruments ever built. Ironically, millions of people have seen it without realizing its remarkable history. Perhaps you've encountered one yourself. A small glass bulb, most of the air removed from its interior. Inside sits a delicate wheel made from 4 lightweight vanes mounted on an almost frictionless spindle. Each vane is black on one side, silver on the other. When sunlight strikes the bulb, the wheel begins to spin. At first glance, the explanation seems obvious. Light pushes harder on one side than the other. The vanes rotate. Radiation pressure confirmed. Crookes himself believed exactly that. To him, this tiny spinning wheel appeared to be the first direct demonstration that Maxwell's prediction was correct. Light was physically pushing matter. It seemed like a triumph, elegant, beautiful, simple. Unfortunately, it was wrong. Not slightly wrong, completely wrong. The strange part was not that the wheel rotated. It absolutely did. The problem was the direction. If radiation pressure truly caused the motion, the silver reflective sides should receive a stronger push than the black absorbing sides. Why? Because when a photon strikes a black surface and is absorbed, it delivers its momentum once. But when a photon strikes a perfect mirror, it bounces backward. Its momentum reverses direction. Changing direction means changing momentum. The mirror therefore receives twice the momentum. Reflection should produce roughly double the push. That means Crookes' vanes should have rotated the opposite way. Yet they didn't. The black sides retreated from the light. The silver sides moved toward it, exactly backward. Something else had to be happening. The answer turned out to be surprisingly subtle. Although Crookes had removed most of the air from inside the glass bulb, he had not removed all of it. A tiny amount remained, far less than ordinary atmospheric pressure, but still enough. When sunlight struck the black surfaces, they absorbed far more energy than the reflective silver sides. The black surfaces became slightly warmer, not dramatically warmer, only enough to heat the remaining gas molecules nearby. Those warmed molecules began bouncing away from the black surfaces slightly faster than molecules bouncing away from the cooler silver sides. Individually, the difference was microscopic. Collectively, billions upon billions of molecular collisions produced a measurable force. The heated gas itself became a tiny invisible engine. The air, not the photons, was pushing the vanes. This phenomenon is known today as thermal transpiration. It had absolutely nothing to do with radiation pressure. Crookes had accidentally invented an incredibly sensitive heat engine instead. The irony is almost poetic. His device became famous precisely because people believed it demonstrated photon momentum. In reality, it demonstrated something entirely different. Even today, inexpensive versions of Crookes radiometers sit on office desks and science museum shelves around the world. People shine flashlights on them. The vanes spin. Many still assume they are watching light physically push the wheel. They aren't. They are watching heated gas molecules perform the work. That misunderstanding persisted for years, and it created genuine confusion among physicists. Some researchers began wondering whether Maxwell's prediction had been mistaken after all. Perhaps radiation pressure simply didn't exist. Others believed the effect might exist in theory, but remained forever impossible to isolate experimentally. Every attempt seemed contaminated by heat. Every measurement seemed vulnerable to hidden air currents. Nature appeared determined to hide the truth. But science often advances because someone becomes obsessed with eliminating every possible source of error. That person arrived at the beginning of the 20th century. His name was Pyotr Lebedev. Unlike Crookes, Lebedev understood exactly what had gone wrong. If radiation pressure truly existed, every competing influence had to disappear, not merely reduced, removed. His apparatus became an extraordinary exercise in patience. He suspended incredibly lightweight mirrors, using delicate fibers inside chambers from which almost every remaining air molecule had been evacuated. He isolated vibrations, controlled temperature, minimized thermal effects, waited for the apparatus to settle, then waited even longer. Every detail mattered, because the force he hoped to measure was almost unimaginably small. If someone coughed nearby, the experiment might fail. If sunlight warmed one side of the apparatus slightly more than the other, the experiment might fail. If a tiny pocket of trapped gas expanded, the experiment might fail. Everything had to become quiet, still, balanced. Only then could the momentum of light reveal itself. Finally, in 1901, Lebedev succeeded. The mirrors moved, not because of heated air, not because of hidden mechanical forces. They moved exactly as Maxwell's equations predicted. Radiation pressure was real. Light pushed. The measured force matched the theoretical value astonishingly well. Around the same time, across the Atlantic, American physicists Ernest Nichols and Gordon Hull independently performed similar experiments using different equipment. Instead of tiny suspended vanes, they used exquisitely sensitive mirrors attached to fine torsion fibers. When light struck the mirrors, they twisted ever so slightly. The amount of twisting revealed the force exerted by the incoming photons. Their measurements agreed with Lebedev's. They also agreed with Maxwell. Three entirely different paths now pointed toward the same conclusion. The mathematics, the Russian experiment, the American experiment, all agreed. Light carries momentum. The evidence had become overwhelming. Yet this success created an even deeper mystery. Scientists now knew that light exerted pressure. They had measured it directly. They had watched matter respond to photons. But one enormous question remained unanswered. How? Maxwell's equations predicted the force. The experiments confirmed it. Neither explained the underlying mechanism in a way ordinary intuition could grasp. How could something with absolutely no mass physically shove an object? What was actually happening during that collision? What did a photon transfer if it possessed no substance? The answer required looking inside light itself, not merely as a wave spreading through space, but as something far stranger, because hidden inside every beam of light was another surprise waiting to overturn physics once again. The story of momentum without mass was only halfway finished. By the beginning of the 20th century, the evidence was no longer in doubt. Light pushed, not metaphorically, not indirectly, not because it heated the air. Photons themselves were transferring momentum to matter. Maxwell's equations had predicted it. Lebedev had measured it. Nichols and Hull had confirmed it. The universe had spoken clearly. Yet a deeper question remained. How does the push actually happen? Imagine standing beside a quiet lake. You throw a stone into the water. Ripples spread outward. Eventually, those ripples reach a floating leaf. The leaf begins to move. That makes intuitive sense. The water itself carries the disturbance. The moving water transfers momentum to the leaf. Everything involved possesses mass. Water pushes water. Water pushes the leaf. Nothing mysterious occurs. Now remove the water. Imagine the ripples crossing completely empty space. No air, no invisible fluid. Nothing. Then imagine those ripples somehow reaching the leaf anyway and pushing it forward. That sounds impossible. Yet something remarkably similar happens every time light strikes matter. There is no material medium carrying light through space. The old idea of an invisible substance called the luminiferous ether had already collapsed under experiment. Light travels through genuine vacuum. Nothing fills the emptiness between the sun and earth. No hidden ocean. No invisible gas. Just space itself. So what exactly reaches an object when light arrives? The answer begins with Maxwell's remarkable picture of electromagnetism. Light is an electromagnetic wave. That phrase is repeated so often that it almost loses its meaning. But it hides an extraordinary reality. A beam of light is not made from tiny pieces of matter flowing through space. Instead, it consists of two invisible fields, an electric field and a magnetic field. These fields oscillate continuously as the wave moves forward. Imagine holding one end of a rope while someone else holds the other. If you snap your wrist, a wave travels along the rope. The rope itself doesn't travel from your hands to theirs. Only the disturbance moves. Every small section simply oscillates up and down, while the overall pattern advances. Electromagnetic waves behave in a strangely similar way, except there is no rope. Instead, the electric and magnetic fields continually regenerate one another. The electric field changes. That changing electric field creates a magnetic field. The magnetic field changes. That changing magnetic field recreates the electric field, again and again and again. The disturbance moves forward at exactly the speed of light. What makes this especially remarkable is that these fields are not pointing in the direction the light travels. The electric field oscillates sideways. The magnetic field oscillates in another sideways direction. The wave itself travels forward. 3 directions, each perfectly perpendicular to the others. This peculiar geometry turns out to be the key. Suppose this electromagnetic wave reaches a solid surface. Perhaps it strikes a tiny metal mirror suspended inside a laboratory. Or perhaps it reaches the atoms inside your skin. What happens first? The electric field begins interacting with charged particles, mostly electrons. Electrons carry negative electric charge, making them extremely sensitive to electric fields. As the wave arrives, the electric field starts pulling those electrons back and forth, not forward, sideways. Imagine holding a spring attached to a small metal ball. Move your hand left and right. The ball follows. The electric field performs something similar. It causes electrons to oscillate rapidly inside the material. If the story ended there, nothing would move forward. The electrons would simply jiggle sideways forever. No radiation pressure, no momentum transfer, no push. This is where the magnetic field quietly enters the story. Unlike electric fields, magnetic fields only exert forces on moving charges. A stationary electron feels nothing from a magnetic field. But an electron already moving because of the electric field suddenly becomes vulnerable. As the oscillating electrons sweep sideways, the magnetic field redirects part of their motion. The result is astonishing. The combined action of the electric and magnetic fields produces a tiny force pointing in exactly the direction the light itself is traveling. Forward. The electric field supplies the motion. The magnetic field redirects it. Together, they create a steady transfer of momentum into the material. This coordinated dance happens billions upon billions of times every second. Every arriving electromagnetic wave continuously repeats the process. The electrons respond. Momentum flows. Matter experiences a push. No hidden substance is required. No secret mass is hiding inside the photon. The fields themselves perform the work. This explains something else that puzzled physicists for decades. Why is the force so incredibly small? The answer lies in the relative strength of those two fields. The electric field strongly influences charged particles. The magnetic field, by comparison, produces much weaker forces under ordinary conditions. Its influence depends upon how quickly those charged particles are already moving. Since the electrons only oscillate over microscopic distances during each cycle of the electromagnetic wave, the magnetic contribution remains tiny. Most of the energy arriving in sunlight simply causes electrons to vibrate. Only a very small fraction becomes forward momentum. Yet that fraction is never zero. Every photon contributes. Every beam pushes. Always. Imagine standing beneath gentle rain. Each raindrop carries a tiny amount of momentum. One drop barely matters. Thousands begin to accumulate. Millions become noticeable. Now imagine replacing every raindrop with something vastly smaller. Photons. Each one delivering a push far weaker than a single raindrop. So weak that trillions must arrive before the effect becomes measurable. Yet they do arrive. Every second. Every hour. Every day. Sunlight continuously bombards Earth with unimaginable numbers of photons. Roughly 170 quadrillion watts of solar energy strike our planet every moment. That energy arrives because photons are continuously streaming outward from the sun in every direction. Each photon possesses only a tiny amount of momentum. Together, they generate a measurable pressure over the entire Earth. Spread across the planet's enormous surface area, the total force amounts to roughly 130 million pounds. At first, that sounds enormous. 130 million pounds. Surely that should be obvious. But numbers without context can be deceptive. Earth's surface covers nearly 200 million square miles. Spread across that unimaginable area, the pressure becomes incredibly weak. Gravity pulling you toward Earth is roughly 1 trillion times stronger than sunlight pushing you away from the sun. The difference is so extreme that your body has no chance of noticing. Gravity completely dominates your everyday experience. Photon momentum quietly goes about its work unnoticed, but scale changes everything. Consider a microscopic dust particle drifting through interplanetary space. Gravity still acts, but now the particle possesses almost no mass. Suddenly, the gentle push of sunlight becomes significant. Given enough time, photon momentum gradually changes its orbit. This is exactly what happens inside comet tails. Now shrink even further. Imagine a single atom floating inside an experimental chamber. Compared to everyday objects, atoms are astonishingly light. A single photon can deliver a measurable kick, not because the photon has become stronger, because the atom has become smaller. This is one of the recurring themes throughout physics. The importance of a force depends not only on its strength, but also on what it acts upon. The same gentle breeze that barely nudges a parked truck can send a soap bubble drifting across a garden. Photon momentum behaves exactly the same way. Against planets, it appears almost insignificant. Against atoms, it becomes transformative. Against enormous reflective sails floating through empty space, it becomes useful propulsion. Against massive stars producing unimaginable floods of radiation, it helps determine whether those stars survive at all. The push of light never changes. Only the scale does. Yet, despite understanding the electromagnetic mechanism, physicists still faced an uncomfortable contradiction. Newton's mechanics insisted momentum belonged to mass. Maxwell's equations, and now direct experiments, showed momentum flowing from something completely massless. Both theories worked astonishingly well. Neither could simply be discarded. For a brief moment, physics found itself balancing between two enormously successful descriptions of reality that appeared impossible to reconcile. Somewhere beneath both theories lay a deeper truth, a truth that would force scientists to rethink not only momentum, but the nature of energy, space, time, and reality itself. The person who would uncover that deeper relationship was not working in a famous university laboratory. He was sitting behind a desk in a Swiss patent office, quietly examining inventions while imagining an entirely different universe. By the early years of the 20th century, physics had reached an uncomfortable crossroads. On one side stood Isaac Newton. For more than 200 years, his laws had described the motion of everything humanity could observe. Planets followed his equations. Cannonballs followed his equations. Falling apples, swinging pendulums, steam engines, ships, bridges, locomotives. Every machine of the Industrial Revolution behaved exactly as Newton predicted. His mathematics seemed almost perfect. On the other side stood James Clerk Maxwell. His equations had unified electricity, magnetism, and light into a single elegant framework. They predicted radio waves before anyone had ever transmitted one. They explained optics, electricity, and magnetism with astonishing precision. His mathematics also seemed almost perfect, and yet the two theories disagreed. Not on a minor detail, on one of the most fundamental ideas in physics. Newton's mechanics implied that momentum belonged to mass. Maxwell's electromagnetism insisted that light possessed momentum despite having no mass whatsoever. Both theories had survived countless experimental tests. Both worked brilliantly. Both could not be completely correct. Somewhere beneath them, a deeper description of reality had to exist. Most physicists searched for complicated explanations. Perhaps light was secretly carrying an invisible substance. Perhaps the mysterious ether still existed after all. Perhaps momentum behaved differently inside electromagnetic fields than it did everywhere else. Every proposed solution attempted to preserve the familiar picture of the universe. Then a young patent clerk ignored the familiar picture completely. Albert Einstein was only 26 years old. He held no prestigious university position. He directed no famous laboratory. During the day, he examined patent applications inside the Swiss patent office in Bern. At night, he thought about physics. His questions were strangely simple. What would happen if you chased a beam of light? What would light look like if you somehow moved beside it at exactly the same speed? The question sounds innocent. Its consequences were anything but. According to Newtonian mechanics, velocities simply add together. Imagine standing inside a train moving 100 kilometers per hour. If you throw a baseball forward at 20 kilometers per hour relative to the train, someone standing beside the tracks sees the ball moving 120 kilometers per hour. Simple addition. Everything works exactly as intuition suggests. For centuries, nobody questioned it. Now replace the baseball with light. Suppose a flashlight shines forward from the front of the train. If Newton's rules apply, someone standing beside the tracks should measure the light traveling faster than someone inside the train. Light should gain the train's speed. It seems perfectly reasonable. Yet every experiment stubbornly refused to agree. The most famous of those experiments had already been performed nearly 20 years earlier by Albert Michelson and Edward Morley. They built one of the most sensitive scientific instruments ever constructed. Its purpose was straightforward: measure Earth's motion through the hypothetical luminiferous ether. If light really traveled through an invisible medium, then Earth should move through that medium as it orbited the sun. Just as a swimmer feels water flowing past while crossing a river, Earth should experience an ether wind. Light traveling with that wind should behave slightly differently from light traveling across it. The difference would be tiny, but Michelson's interferometer was sensitive enough to detect it. The experiment was repeated, again and again, at different times of day, during different seasons, as Earth changed direction throughout its orbit. Every result said exactly the same thing. Nothing. No ether wind, no change, no preferred direction. Light always traveled at precisely the same speed. It didn't matter whether Earth moved toward the beam, away from it, or sideways. The speed remained constant. Physicists found this deeply disturbing, because if the speed of light never changes, then something far stranger must. Einstein realized that everyone had been protecting the wrong assumption. Scientists desperately tried to preserve absolute space, absolute time, absolute motion. Instead, Einstein proposed something radical. What if those were the things that changed? He built his theory upon only two simple principles. First, the laws of physics are identical for every observer moving at constant velocity. There is no special place in the universe, no privileged frame of reference, no cosmic stage against which everything else moves. Second, the speed of light in a vacuum is always the same, not approximately, exactly. No matter how fast the observer moves, no matter how fast the source moves, light always travels at the same speed. At first, these two statements seem harmless, almost obvious, but together they force reality into doing something astonishing. Imagine two people, one standing on Earth, another riding aboard an unimaginably fast spacecraft. Each carries an identical clock. Each shines an identical flashlight. Each measures the speed of light. Both obtain exactly the same answer: 300,000 kilometers every second. How can that possibly happen? If the speed remains fixed, then distances and time themselves must adjust. This was Einstein's extraordinary insight. Space is not absolute. Time is not absolute. They stretch, they contract, they adapt so that the speed of light remains constant for everyone. Suddenly, familiar concepts began behaving in unfamiliar ways. Moving clocks tick more slowly. Moving rulers become shorter. Events occurring simultaneously for one observer may occur at different moments for another. These ideas sounded almost absurd, yet experiment after experiment confirmed them. Today, they are no longer theoretical curiosities. They are engineering necessities. Every GPS satellite orbiting Earth experiences time slightly differently than clocks on the ground. Its motion slows time. Earth's weaker gravity speeds time up again. Engineers must account for both effects simultaneously, ignore relativity, and GPS positions drift by kilometers every single day. Your smartphone works because Einstein was right. Particle accelerators reveal the same reality. Tiny, unstable particles created during collisions should decay almost instantly. According to Newtonian intuition, they should vanish before traveling significant distances. Instead, moving at speeds extremely close to light, their internal clocks run slower. They survive many times longer than expected. Scientists observe them reaching detectors they should never have reached, again and again. Reality quietly confirms Einstein. The universe simply does not obey Newton's assumptions once velocities become sufficiently large. Momentum changes too. The familiar equation, momentum equals mass times velocity, turns out not to be wrong, but incomplete. It works beautifully for ordinary speeds: cars, baseballs, airplanes, even rockets, all move so slowly compared with light that Newton's equation becomes an extraordinarily accurate approximation. But as objects approach light speed, the approximation begins breaking down. Eventually, it fails completely, especially for light itself. Einstein replaced Newton's simple picture with something far deeper. Momentum no longer depended merely upon mass. Instead, momentum became inseparably linked with energy, not as two unrelated quantities, but as different aspects of the same underlying reality. Most people know Einstein because of a single equation, E equals mc squared. Perhaps no equation in history has become more famous. It appears in films, on t-shirts, in cartoons. Yet surprisingly few people know what it actually means. Even fewer realize it is not Einstein's complete equation. It is merely a special case, a simplified version, one piece of a much larger picture. Because the real relationship connecting energy, momentum, and mass is considerably richer. And hidden inside that larger equation lies the explanation physicists had been searching for ever since Maxwell predicted radiation pressure. The explanation for how something completely massless can carry momentum. The answer had been waiting inside Einstein's mathematics all along. Most people recognize Einstein's famous equation instantly, E equals mc squared. It has become a symbol of genius itself, printed on coffee mugs, written across classroom walls, referenced in films, television shows, and popular culture. Yet, despite its fame, the equation is almost always misunderstood. People often believe it says that mass can become energy, or that energy can become mass. Those ideas are true, but they are only part of the story. In reality, E equals mc squared is not Einstein's complete equation. It is a simplified version, a special case, one that only applies when something is completely at rest. Imagine placing a baseball on a table. It isn't moving. It possesses no kinetic energy, no momentum. Yet according to Einstein, it still contains an enormous amount of energy, not because anything unusual is happening, simply because it has mass. Every atom inside that baseball stores energy, merely by existing. That hidden reservoir is what E equals mc squared describes. The equation tells us that mass itself is a form of energy. The amount is astonishing. Even a tiny amount of matter contains tremendous energy because the speed of light squared is an unimaginably large number. This is the principle behind nuclear power. It is the reason stars shine. Inside the sun, tiny amounts of mass disappear during nuclear fusion. That missing mass does not vanish. It becomes energy. The sunlight warming your face today was once locked inside atomic nuclei deep within the sun's core. For a stationary object, Einstein's famous equation tells the whole story. But the moment something begins moving, another ingredient appears: momentum. And this is where the complete equation enters. Instead of writing only E equals mc squared, Einstein showed that the deeper relationship is E squared equals pc squared plus mc squared. At first glance, it looks intimidating, yet its meaning is surprisingly beautiful. The total energy of anything in the universe comes from two possible sources. One part comes from mass, the other comes from momentum. Both contribute. Both are equally fundamental. Think of it like a right triangle. One side represents energy associated with mass. Another side represents energy associated with momentum. Together they determine the total energy. Nothing is missing. Everything fits. For ordinary objects, both terms exist. A moving car possesses mass. It also possesses momentum. Its total energy combines both contributions. Nothing surprising happens. But now imagine something extraordinary. Imagine setting the mass equal to zero. Exactly zero. Not almost zero, precisely zero. One entire side of the equation disappears. The relationship suddenly becomes dramatically simpler. The equation becomes E squared equals pc squared. Take the square root. Now it reads E equals pc. Rearrange it slightly. Momentum equals energy divided by the speed of light. P equals E over c. There it is, the mystery that puzzled physicists for centuries. Momentum does not fundamentally require mass. It requires energy. Light carries energy. Therefore, light carries momentum. Not because photons secretly possess hidden mass. Not because Newton's laws somehow stop working, but because Newton's equation was never the deepest description of reality. Mass is only one way to possess energy. Light uses another. This realization changes the way we should think about almost everything. For centuries, scientists believed momentum belonged to matter, because every object they encountered happened to contain mass. Rocks, trees, birds, people, planets. Everything carrying momentum also carried mass. The connection appeared perfect, but appearances can deceive. Imagine someone who has lived their entire life near rivers. Every river they have ever seen contains water. Eventually, they conclude that rivers and water are inseparable. Then one day they discover lava flowing down the side of a volcano. It follows valleys. It bends around hills. It behaves remarkably like a river, except it isn't water. The original conclusion wasn't exactly wrong. It was incomplete. Water is one way to create a river, not the only way. Mass is one way to carry energy, not the only way. Light revealed another. This distinction seems subtle. In reality, it changes everything. Because once momentum belongs to energy instead of mass, the universe suddenly becomes far more unified. The same mathematical relationship now describes bowling balls and photons, planets and radio waves, electrons and gamma rays. Everything fits within one framework. Nature no longer needs separate rules. One equation governs all of them. This is one of the recurring themes throughout modern physics. As our understanding deepens, different phenomena begin merging together. Electricity and magnetism become electromagnetism. Space and time become spacetime. Mass and energy become equivalent. Momentum and energy become inseparable. Instead of accumulating more laws, physics often discovers fewer, more general, more elegant, more powerful. At this point, some people ask an obvious question. If light has energy, doesn't that mean it really does have mass after all? The confusion is understandable. For many years, physicists themselves sometimes described something called relativistic mass. According to this older idea, an object's energy could be interpreted as an increase in mass. People even spoke of photons possessing an effective mass because they carried energy. Today, most physicists avoid this language, not because it is entirely wrong, but because it easily creates misunderstanding. Photons do not gain mass while moving. They do not hide invisible mass inside themselves. Their rest mass remains exactly zero, always. The equation already explains everything without inventing additional concepts. A photon carries energy. Energy carries momentum. Nothing else is required. This seemingly small clarification matters enormously. Imagine calling a bank account money mass. Technically, your account contains purchasing power, but describing it as mass would only create confusion. It is simpler to call it what it actually is. Energy behaves similarly. Energy contributes to momentum directly. No hidden mass needs to appear. The photon remains exactly what experiments say it is, a genuinely massless particle, yet one carrying perfectly real momentum. Perhaps the most beautiful consequence of Einstein's equation is how inevitable everything suddenly becomes. Before relativity, photon momentum appeared almost miraculous. After relativity, it becomes unavoidable. If energy exists, momentum follows. The mathematics leaves no alternative. The universe simply refuses to separate the two. That realization solved one mystery, but another had quietly emerged. Everything discussed so far still treated light primarily as a wave, Maxwell's wave, an oscillation of electric and magnetic fields spreading through space. Radiation pressure naturally emerged from that picture. Yet during exactly the same years, Einstein was developing relativity. Another revolution was beginning, one that would reveal light to be something even stranger. Not merely a wave, but a stream of individual particles called photons. And each one, every single photon crossing the universe, carries its own precise, measurable amount of momentum, not an average, not an approximation, an exact quantity. Scientists would soon find a way to watch individual photons transfer that momentum, one collision at a time. And when they did, the impossible became undeniable. For most of the 19th century, physicists believed the mystery of light had already been solved. Maxwell's equations were extraordinarily successful. They explained reflection, refraction, polarization, interference, diffraction. Every phenomenon seemed to point toward the same conclusion. Light was a wave. Case closed. The wave picture worked so beautifully that almost nobody imagined it could be incomplete. After all, waves produce interference patterns. They bend around obstacles. They spread through space. Light did all of those things. What more could there be to discover? Yet nature has a peculiar habit of refusing to fit inside a single picture. Every time physicists became convinced they had reached the final explanation, reality quietly revealed another layer beneath it. This time, the clue came from something surprisingly ordinary: a piece of metal. Imagine shining light onto a polished metal surface. Nothing dramatic seems to happen. The metal becomes slightly warmer. Perhaps it reflects part of the light. Perhaps it appears brighter. Nothing seems mysterious. Now imagine performing the same experiment inside an extremely sensitive laboratory. Instead of simply observing the surface, you carefully monitor its electrons. Suddenly, something remarkable appears. Electrons begin leaving the metal. They are literally ejected from the surface. Light is knocking them free. This phenomenon became known as the photoelectric effect. At first, physicists assumed the explanation would be straightforward. Light is a wave. Waves carry energy. Brighter light carries more energy. Therefore, brighter light should gradually deliver enough energy to knock electrons loose. It seemed perfectly reasonable, but the experiments refused to cooperate. Suppose you shine an extremely bright red light onto a metal surface. According to the wave picture, the enormous amount of energy should eventually free electrons. Perhaps not immediately, but after enough time, the energy ought to accumulate. Yet nothing happened. No matter how bright the red light became, some metals refused to emit a single electron. Now replace that brilliant red light with a very faint ultraviolet light. Instantly, electrons began flying out. This made no sense. The ultraviolet beam carried far less total energy than the brilliant red beam. Why should the weaker light succeed where the stronger one failed? Even stranger, increasing the brightness of ultraviolet light produced more electrons, but each electron emerged with exactly the same energy. Brightness affected quantity, not quality. The behavior contradicted everything expected from ordinary waves. Something deeper was happening. In 1905, the same astonishing year he published Special Relativity, Albert Einstein proposed an explanation so radical that many physicists rejected it immediately. Perhaps light was not merely a continuous wave. Perhaps it arrived in individual packets, tiny, discrete bundles of energy, each bundle behaving almost like a particle. Today, we call these bundles photons. The idea itself wasn't entirely new. A few years earlier, Max Planck had introduced energy quanta while studying thermal radiation. Planck viewed them mainly as a mathematical trick. Einstein took the idea seriously. He suggested that light itself genuinely consisted of individual quanta. Each photon carried one precise amount of energy, nothing more, nothing less. That energy depended entirely upon the light's frequency. The relationship was astonishingly simple. Energy equals Planck's constant multiplied by frequency. One tiny equation, one tiny constant. Yet together they transformed physics forever. Higher frequency light meant higher energy photons. Lower frequency light meant lower energy photons. Blue photons carried more energy than red photons. Ultraviolet photons carried far more than visible light. Gamma rays carried vastly more still. Suddenly, the photoelectric effect became obvious. An electron inside a metal requires a minimum amount of energy to escape. If a photon possesses enough energy, the electron leaves immediately. If the photon lacks sufficient energy, nothing happens. No amount of waiting changes the outcome. No accumulation occurs. One photon interacts with one electron. Either it succeeds, or it doesn't. Brightness merely changes how many photons arrive every second. More photons free more electrons. But each individual interaction remains exactly the same. The experiments fit Einstein's explanation perfectly. Every observation suddenly made sense. The photoelectric effect became one of the first great triumphs of quantum physics. Einstein would later receive the Nobel Prize not for relativity, but for explaining this phenomenon. Now something extraordinary happened. Two seemingly unrelated ideas collided. Special relativity had already shown that, for a massless particle, momentum equals energy divided by the speed of light. Quantum theory had shown that each photon carries energy, determined by its frequency. Place those two discoveries together. The result is inevitable. If energy equals Planck's constant multiplied by frequency, and momentum equals energy divided by the speed of light, then every photon possesses its own precise momentum, not an average, not merely the momentum of the beam as a whole. Each individual photon carries its own tiny packet of momentum. The equation becomes beautifully simple. Momentum equals Planck's constant divided by wavelength. Everything depends upon wavelength. Short wavelengths mean greater momentum. Long wavelengths mean less. A gamma-ray photon carries vastly more momentum than a visible light photon. A blue photon carries slightly more momentum than a red one. Nothing mysterious remains. Every photon arrives carrying a definite amount of energy, a definite amount of momentum, both determined entirely by its frequency. This was an astonishing realization. For centuries, momentum had belonged to visible objects. Now it belonged equally to invisible particles of light. But theory alone was never enough. Physicists wanted evidence, direct evidence. Could anyone actually observe a single photon transferring its momentum during an individual collision? Could the process be measured? Could the tiny kick from one photon be caught in the act? The answer arrived in 1923. An American physicist named Arthur Compton designed one of the most elegant experiments in scientific history. Instead of visible light, he used X-rays. X-ray photons carry far more energy than ordinary light. More importantly, they carry far more momentum. Compton directed these photons toward electrons inside graphite. When the photons struck the electrons, something remarkable happened. The photons scattered away, but they did not leave unchanged. After each collision, their wavelength increased, their frequency decreased, their energy dropped. Where had that missing energy gone? Into the electron. The electron recoiled exactly as though it had been struck by a tiny projectile. Even more remarkable, the amount by which the photon's wavelength changed depended precisely upon the scattering angle. Compton calculated the expected result by treating the photon exactly like a particle carrying momentum. His equations predicted the wavelength shifts perfectly. Every measurement matched. Photon after photon behaved exactly like tiny packets of momentum colliding with electrons. Not metaphorically, literally. It was impossible to dismiss. The wave picture remained correct. Interference still existed. Diffraction still existed. Maxwell's equations still described light beautifully. But another picture had become equally unavoidable. Light also behaved like particles. Each photon carried a precise amount of momentum. Each collision conserved both energy and momentum exactly as relativity demanded. Nature had once again refused to choose between two human categories. Light was not simply a wave, nor simply a particle. It possessed characteristics of both. Depending on the experiment, one aspect became visible, while the other quietly receded into the background. The deeper reality lay beneath both descriptions. And perhaps the most astonishing consequence had not yet appeared. Because once physicists accepted that waves could behave like particles, another question naturally emerged. What if particles could behave like waves? Arthur Compton's experiment settled one question beyond any reasonable doubt. Individual photons carried individual momentum. They collided with electrons. They transferred energy. They recoiled exactly as conservation laws demanded. Light behaved like a stream of particles. For many physicists, The story should have ended there. The universe had revealed that light was stranger than anyone had imagined. A wave that sometimes behaved like a particle, an electromagnetic disturbance made of individual quanta called photons. Surely that was extraordinary enough. But science has a habit of asking dangerous questions. Questions that begin with only two words. What if? In 1924, a young French physicist named Louis de Broglie asked one of the boldest questions ever proposed in theoretical physics. If waves can behave like particles, could particles behave like waves? At first, the idea sounded almost ridiculous. Electrons were particles. Everyone knew that. They possessed mass. They could be accelerated by electric fields. They curved inside magnetic fields. They left tracks inside cloud chambers. Everything about them suggested tiny, solid objects moving through space. Nothing about an electron resembled a wave on water. Nothing resembled light. Yet neither had photons until nature insisted otherwise. De Broglie noticed something profound. The equation describing photon momentum was astonishingly elegant. Momentum equals Planck's constant divided by wavelength. Nothing inside that equation specifically referred to light. Nothing required photons. Nothing demanded electromagnetic waves. The relationship simply connected momentum and wavelength. So de Broglie wondered, perhaps this equation applies to everything, not just light. Every moving object, every particle, every atom, every molecule, everything possessing momentum. According to his proposal, every particle has an associated wavelength. A moving electron should possess one. A proton should possess one. Even a baseball should possess one. Immediately, people objected. Surely that couldn't be right. If baseballs behaved like waves, why don't they spread out like ripples across a pond? Why don't people interfere with themselves while walking through doorways? Why don't cars diffract around corners? The answer lay inside Planck's constant. It is astonishingly small. For ordinary objects, the associated wavelength becomes so unimaginably tiny that every wave-like effect disappears completely. A baseball does possess a wavelength. It is simply so microscopic that no conceivable experiment could detect it. Electrons, however, are different. Their momentum is tiny. Their wavelength becomes large enough to observe. Still, an equation alone proves nothing. Nature would decide. 3 years later, in 1927, physicists Clinton Davison and Lester Germer accidentally performed one of the most important experiments in modern science. Interestingly, they weren't even trying to test de Broglie's idea. They were studying how electrons scattered from metal surfaces. During the course of their work, part of their equipment became damaged. After repairing it, they repeated the experiment. The results surprised everyone. Instead of scattering randomly like tiny bullets, the electrons produced an interference pattern. Bright regions, dark regions, alternating bands. Exactly the pattern expected from waves, not particles. Waves. The electrons had diffracted. They had spread through space. They had interfered with themselves. Most astonishing of all, the measured wavelength matched de Broglie's prediction perfectly. The equation was right. Matter possessed wave properties, not metaphorically, not approximately, literally. The implications were breathtaking. Everything in the universe suddenly belonged to one unified picture. Photons behaved like particles. Particles behaved like waves. Momentum connected them both. The same equation described each. Nature had quietly erased another boundary. For centuries, humanity separated reality into categories: matter, energy, particles, waves. Each seemed fundamentally different. Quantum mechanics revealed that these distinctions were often matters of perspective rather than absolute truth. The deeper reality lay underneath. This also changed how physicists viewed photon momentum. Earlier generations sometimes regarded it as an exception, a curious loophole applying only to light. Now it became something much more profound. Photon momentum was simply one example of a universal relationship connecting motion and wavelength throughout the universe. Everything moving possessed momentum. Everything possessing momentum possessed wave-like properties. The same mathematical structure governed both massive particles and massless photons. Nature preferred unity over exceptions. Perhaps the most beautiful consequence of this realization is how elegantly different theories suddenly fit together. Maxwell explained light as electromagnetic waves. Einstein explained why energy carries momentum. Quantum mechanics explained why light arrives as photons. De Broglie extended the relationship to matter itself. Instead of contradicting one another, these ideas formed different pieces of a single extraordinary puzzle. Each theory illuminated part of reality. Together, they described something deeper than any could alone. Of course, all this discussion of wavelengths and momentum can make photon momentum seem almost abstract. An elegant equation, a beautiful mathematical relationship, something existing mainly inside textbooks. Yet photon momentum is anything but abstract. It can be measured, used, engineered, harnessed. Let's appreciate just how tiny a single photon's momentum actually is. Take an ordinary green photon. Its wavelength is roughly 550 nanometers. Using the equation momentum equals Planck's constant divided by wavelength, its momentum works out to approximately 1.2 times 10 to the minus 27 kilogram meters per second. That number is almost impossible to imagine. Compare it with something familiar. A tiny fruit fly weighing about 1 milligram and flying at only 1 meter per second possesses roughly 10 to the power of minus 6 kilogram meters per second of momentum. The fly carries about 1 billion trillion times more momentum than one visible photon. A single photon is unbelievably gentle. Its push is so small that no human being could ever hope to feel it directly. No ordinary object could respond noticeably. No scale could weigh it. No finger could sense it. And yet, photons almost never travel alone. Turn on an ordinary 60-watt light bulb. Every second, it emits roughly 100 quintillion photons. Not thousands, not millions, not billions. 100 quintillion every second. Each carries its tiny momentum, individually meaningless, collectively measurable. Nature often works this way. One snowflake weighs almost nothing. An avalanche can bury a mountain. One raindrop barely disturbs a pond. A flood reshapes landscapes. One photon cannot move anything visible. Trillions upon trillions arriving together become a real mechanical force. That simple fact would soon allow physicists to accomplish something that would have seemed completely impossible only a few decades earlier. They would begin controlling matter, using nothing but light itself. By now, the mystery that began this journey has almost completely transformed. At first, it seemed impossible that something without mass could ever push on anything. Then we discovered that momentum belongs not to mass, but to energy. We learned that every photon carries a precise amount of momentum, determined entirely by its wavelength. We watched photons collide with electrons. We saw light reveal both its wave nature and its particle nature. What once looked like a paradox became an inevitable consequence of the deepest laws of relativity and quantum mechanics. But perhaps the most satisfying part of this story is that photon momentum is not merely a beautiful idea hidden inside equations. Humanity has learned to use it. One of the most remarkable examples is something known as laser cooling. At first glance, the phrase almost sounds contradictory. Lasers produce light. Light carries energy. Energy usually heats things. So how can light possibly make something colder? The answer lies entirely in momentum. Imagine a single atom drifting through an almost perfect vacuum. It moves only because of its own motion. There is no air slowing it down, no friction, nothing to rob it of speed. Now imagine pointing a laser directly toward that atom. If the atom happens to be moving toward the incoming photons, something extraordinary occurs. Eventually, one of those photons is absorbed. The atom gains the photon's energy, but it also gains the photon's momentum. Since the photon was traveling opposite the atom's motion, that momentum acts like a tiny brake. The atom slows down ever so slightly. Afterward, the atom emits another photon. That photon leaves in a random direction. Over millions of absorption and emission events, those random emissions average out. but every absorbed photon consistently pushes against the atom's motion, again and again and again. The atom becomes slower. Its kinetic energy decreases. Its temperature falls. Eventually, scientists can cool entire clouds of atoms to temperatures only millionths or even billionths of a degree above absolute zero, not by removing heat directly, but by using the momentum of light itself. Think about how astonishing that really is. A photon possesses no mass. Its individual momentum is unimaginably tiny. Yet trillions of carefully controlled photon collisions can gradually bring moving atoms almost completely to rest. Some of the coldest places ever created in the history of the universe exist inside laboratories on Earth, not because scientists discovered a magical refrigerant, because they learned how to aim photon momentum with extraordinary precision. These ultra-cold atoms have become essential tools in modern science. They allow physicists to build atomic clocks so accurate they would lose less than a second over billions of years. They make quantum computers possible. They allow experiments probing the deepest foundations of reality. Once again, everything begins with a simple fact: light pushes. Another remarkable technology takes the same idea even further. Instead of merely slowing microscopic objects, scientists learned to hold them completely still. Imagine trying to pick up a single living cell, or a tiny bacterium, or an individual strand of DNA. Even the finest mechanical tweezers would crush them instantly. They are simply too small, too fragile. Arthur Ashkin realized something extraordinary. Perhaps tweezers didn't need to be made from metal. Perhaps they could be made from light. He focused a powerful laser into an incredibly tiny point. As photons passed through a microscopic transparent object, they bent slightly because of refraction. Whenever a photon's direction changes, its momentum changes. Conservation of momentum demands that something else receive an equal and opposite change. That something is the tiny particle itself. If the particle drifts away from the center of the laser beam, the bending photons gently push it back. Move left, the photons push right. Move upward, the photons push downward. The result is astonishing. The particle becomes trapped inside a cage made entirely of light. Not because the laser burns it, not because it sticks to anything, simply because billions of photons continuously exchange momentum with it. Scientists call these devices optical tweezers. Today, they are used throughout biology and medicine. Researchers manipulate individual viruses, move living cells one at a time, stretch DNA molecules, measure the tiny forces produced by proteins inside living organisms, all without ever touching them. Instead, they let light do the touching. Again, photon momentum quietly performs the work. The same principle also allows humanity to dream much farther from Earth. Imagine unfurling an enormous mirror in space. No engine, no fuel, no exhaust. Just an enormous, ultra-thin, reflective sail stretching hundreds of meters across. Now point it toward the sun. Every arriving photon strikes the reflective surface. Instead of being absorbed, it bounces away. That reflection doubles the momentum transferred to the sail. One photon contributes almost nothing, but sunlight contains incomprehensible numbers of photons. Every second, the sail receives another push, and another, and another. There is no friction in space, no air resistance, no rolling resistance, no engine that eventually runs out of propellant. The acceleration is tiny, but it never stops. Day after day, month after month, year after year. Eventually, the spacecraft reaches speeds impossible for conventional rockets to maintain. This is the principle behind solar sails. Unlike ordinary spacecraft, they carry no fuel for propulsion. Their engine is sunlight itself. In 2010, Japan successfully demonstrated this idea with the spacecraft Icaros. Its enormous reflective sail captured the momentum of sunlight and used it to alter its trajectory through interplanetary space. Later, LightSail 2 demonstrated the same principle in Earth orbit. These missions were modest, proofs of concept, yet they confirmed something humanity had once considered impossible. Spacecraft can genuinely sail on light. Perhaps the boldest proposal of all is breakthrough starshot. The idea sounds almost like science fiction. Instead of relying on sunlight, an enormous array of powerful lasers on Earth would illuminate a tiny reflective sail attached to an equally tiny spacecraft. The lasers would deliver an unimaginable flood of photons. Each photon contributes only its tiny momentum. Together, they would accelerate the spacecraft to nearly 20% of the speed of light, fast enough to reach the nearest star system, Proxima Centauri, in roughly 20 years. Whether such a mission will ever succeed remains uncertain. The engineering challenges are immense. The laser array would consume staggering amounts of energy. The sail must survive extraordinary heating. The spacecraft must survive decades alone in interstellar space. Yet, the underlying physics requires no speculation. Photon momentum is sufficient. The equations work. Nature permits it. The only remaining challenge is engineering. There is something deeply satisfying about this progression. The same tiny momentum that gently nudges dust away from a comet also cools atoms to temperatures near absolute zero. The same momentum that twists microscopic mirrors inside laboratories may someday carry humanity's first probes to another star. The scale changes dramatically. The physics never does. Every photon obeys the same equations. Every collision conserves the same momentum. Every interaction follows the same elegant laws discovered more than a century ago. When we first began this journey, light appeared almost ghost-like, something that illuminated reality without participating in it. Now the picture looks completely different. Light shapes the universe. It pushes. It transfers motion. It balances gravity inside massive stars. It sculpts comet tails. It manipulates atoms. It traps living cells. It propels spacecraft. It is not merely a messenger carrying information across space. It is one of the universe's most active physical agents. And perhaps that is the deepest lesson hidden inside this remarkable story. Human intuition told us that pushing requires mass. Nature quietly disagreed. Momentum belongs to something even more fundamental: energy. Mass simply happens to be one of its most familiar forms. Light reminded us that reality is often far stranger and far more elegant than everyday experience suggests. The next time sunlight falls across your face, remember what is truly happening. An endless river of massless photons has traveled for more than 8 minutes across empty space. Each one carries a tiny packet of energy. Each one carries a tiny packet of momentum. Each one delivers an almost unimaginably gentle push before disappearing forever. You will never feel that force. Yet without it, comets would look different. Lasers could not trap atoms. Solar sails would never fly. And some of the most massive stars in the universe might not survive at all. Sometimes the smallest forces shape the largest stories. And sometimes the deepest truths about reality arrive carried by something that weighs absolutely nothing. If you enjoyed this slow journey into one of physics' most beautiful mysteries, consider subscribing to Science Sleep Theory. There are many more quiet questions waiting beneath the surface of the universe, and we'll continue exploring them together, one peaceful mystery at a time.